Okay, let's get to the main event, the mean value theorem. It is quite a lot like Rolle's theorem. In fact, it has some of the same premises. So I have a function. It needs to be continuous on a closed interval, and it needs to be differentiable on the open interval. But we don't need to worry about the endpoints being the same anymore. So what the mean value theorem tells me is that there exists some c in AB, some interior point, such that, and this gets a little bit weirder, f prime of c, the derivative there, is equal to the average rate of change. So what is the average rate of change? It is f of b minus f of a, this is my change in my y value, over b minus a, the change in my x value. We've seen this so many times in this course. In fact, let's go ahead and put a little note here. This is just delta y over delta x. Okay, so somewhere it has to actually be going the average rate of change, or the slope of that secant line. And here's my beautiful picture again of, here's two endpoints, a nice continuous differentiable function, a nice continuous differentiable function. Here's the secant line, whose slope is the average rate of change, or in other words, the slope is f of b minus f of a over b minus a. And then here's a tangent line at some point where the x value is c that has the same slope, that same rate of change. Cool. Let's just do a very straightforward example of it with another polynomial. Let's check x cubed minus 5. Well, this is continuous because it's a polynomial. It is definitely differentiable because it's a polynomial. So the mean value must apply. Let's go ahead and see what this would say. It says for some c, in 0, 2, f prime of c equals, well, it's going to equal the average rate of change. I need to figure out what that is. I'm going to plug in 2, so I get 8 minus 5 is a 3. I'm going to plug in 0, and I get minus 5, all over 2 minus 0. Or in other words, 8 over 2 is equal to 4. Okay. That's that average rate of change. Let's go ahead and see if we can find it. Let's find that particular c. Or maybe there might even be more than one, but we'll find one of them. So to do that, I would need to take a derivative. Not so bad. 3x squared. I can do that pretty fast. And I'm going to say, where is that equal to 4? 4 is equal to 3x squared. Well, that's when 1 is equal to x squared. So x is equal to plus or minus 1. But only one of those is actually in the domain I care about. I'm going to keep x equals 1. So in other words, c is equal to 1. And get rid of this one right here. Yep. That's where that happens. Oftentimes we can't find it, or we're using this more theoretically. Okay, I skipped a little note up above, which is that sometimes you'll see this written as f prime of c times b minus a is equal to f of b minus f of a, and I'm actually going to use that in a minute. I find that a little bit less intuitive, but you can see it follows just by multiplying the denominator over. Okay, so the derivative times the change in x should be equal to the change in y at some magic point. Great. That is this in action. Let's do maybe another example that is more intuitive, less mathy. So if I drive 300 miles in 3 hours, well, how fast am I going then? On average, I'm going 100 miles an hour. So I must have been driving 100 miles per hour at some time. It's like when I just got my driver's license and my mom was worried that I got home too fast. She knew that if my average speed was fast, then at some point I needed to be going at least my average speed. All right, so intuitively, this is kind of what's happening in this mean value theorem. And sometimes there's this gap between what we can prove in math and what our intuition is, and sometimes there's a bigger gap where intuition is wrong. When you start getting all kinds of multi-valued functions, or multivariate functions rather, things like the mean value theorem can be all you have to cling on to, because our intuition starts to fail very rapidly. But we give you examples that use your intuition to show you that this is reasonable. Okay. I told you this is an analysis topic. Let's go ahead and see if we can prove this thing. Let's walk through a proof. So the goal here is to make the mean value theorem look like Rolle's theorem, and then use Rolle's theorem. We want to make a function that satisfies Rolle's theorem, and here's what I'm going to do. I'm going to make this h of x is equal to my original function, f of x, right there, and then I want to just subtract off a line that has the same slope. This is a great big old constant that is the average rate of change. And then this is just x minus a, make sure that it is 0 at a. And so this gives me the equation of a line with the same rate of change as I have on average. And the point here is that if I subtract out the average rate of change, I get something that looks more like Rolle's theorem, where the beginning and the end look the same. So notice, if I plug in a into h, I get f of a, because this term goes away. And notice if I plug in b, well, with a little bit of simplifying, I get f of a. So, at a and b, h has the same y value. And we did that so that we could apply Rolle's theorem, which tells us there is some c, there is some point in between a and b, where the derivative is 0. Next up, we want to actually plug that in. So the derivative of h, we can actually compute. And if I do it and I clean it up just a little bit, I just get f prime minus this constant here is just the slope of that line. But now let's plug in that magic c. If I plug in that magic c, I get this expression, remembering that this whole f of b minus f of a over b minus a is just a constant, so plugging in c does nothing. And that should equal 0 by Rolle's theorem. But now we just solve. And lo and behold, what we get out is the result from the mean value theorem. Okay, and then we're going to go ahead and say, yeah, therefore this satisfies the statement of the theorem. And by the way, some of you have seen that you end proofs with QED. People don't really do that anymore. That was an old Latin thing. Usually people just end a proof with a nice like filled in square is really common these days. Okay, so just to back up, what on earth did we do? We wanted to use Rolle's theorem, so we took our function and we just subtracted off a line, so that in such a way that that the new function would satisfy Rolle's theorem. And from there, it was easy peasy. I just plugged in and solved. All right, the ideas of proofs stick with you much longer than usually the theorems or the proofs themselves. And walking through this is really good practice on thinking about what does it mean to write a reasonable proof. It's a hard skill to learn, but if you can learn to do it, you probably can write technical arguments convincingly. And if you can do that, then people will want to have you around for when things get a little bit dirtier, a little bit messier, or they need that extra rigor. That's it for this video. In the next one, we will get a nice application to some stuff from mainly calculus 2.